Recording? Okay, good. So today we're going to go through 5.1, the remaining part of our 5.1. Just a quick recap. Electric field strength is a word starting with V. Vector, and vector has magnitude and direction. And what's the equation for electric field strength? It's Gm upon R square, right? Kq upon R square, yes, correct. And then the force, remember, is QE, which is equals to Q upon R square. Someone asked whether the Q, big Q, small q matters. It doesn't matter lah. You want to put it as alpha 1, alpha 2 also can, so long as you understand that it's two charges. Now, something very important at the end of the lesson that I went through is that that the forces on both charges, even one has 1 megacoulomb, the other one has 1 nanocoulomb, the two forces are the same. They're always equal and opposite. And if you actually think about this, it's actually quite amazing. The forces in this universe comes always in pairs. There will never be a case where you can have a force without the other force. It always comes in pair. And if you think about it, that's the reason why momentum is conserved. If you actually have a force existing without the other force, momentum can not conserve. Understand? So there are certain fundamental principles that are tied to each other. And it's very interesting to see how they tie with each other. Okay? Now, the next thing I'm going to go to is about energy. We have dealt with forces. So how about energy? Now let's deal with something that you're more familiar with. You have seen this kind of battery that looks like this, and then it says 9 volts here, right? Have you seen a 9 volt battery before in your life? You have, right? Okay, good. Have anyone seen a 12 volt battery?
Yes.
Yes? Where? Sorry? WhatsApp images. WhatsApp images. 12 volts batteries are usually used in cars, accumulators. Have you seen a 240 volts battery? Actually, it's right in front of you, or right beside you. Exactly, power supply. The one beside you, or those of you on the right side, it's on your left. Those of you on the left side, is on your right. It's actually a 240 volt supply over there. Don't try to put your fingers into there. Yeah. I tried when I was young, and probably that's why I become who I am now. You may want to try, you may go to the other side. Yeah, you may go to the other side. Yes, Shannon, don't try. You never know which wire in your mind is going to short circuit. Okay, so if it is 9 volts over here, what does it mean? Right? We know the bigger the number, the more powerful, right? But what does it mean? Now, the definition is, we can understand these volts by looking at this equation. This is how potential difference, as we will know it later, is defined. Now, applied to the context of a circuit, basically 9 volts means 9 joules of energy. The equivalent for this is W. When 1 coulomb, this is your Q, of charge, 9 joules of energy is supplied by the battery when 1 coulomb of charge is driven through the circuit. So whenever we say volts, you need to straight away link to energy. It is energy. It is not forces. It has to do with energy. The bigger some people like to say voltage, although I don't like to say that. I like to say EMF of the battery. The more energy the battery supplies whenever it drives 1 coulomb of charge around. That's what it means. Alright? So that is to say, W, if I want to find the work done, I just take the potential difference multiplied by the EMF of the battery multiplied by the charge that it supplies. Okay? Can I safely assume that all of you know this equation, I equals to Q upon T? Now, I will leave the definition of current 1 ampere later. Some of you may think that 1 ampere is being defined as 1 coulomb of charge flowing through a point per unit time. It is not. I will come to that when we do 5.4. The definition of ampere has to do with magnetic field. I'll KIV that for a while. Let's park it for a while, but let's understand the current as the rate of flow of charges. Q upon T. So let's do a simple question, a very simple one, and see whether you can connect these two equations and use them in a relevant way. To get your mind warmed up. This is A, this is V, this is 3 volts, and this is 0.2 M. Find question number 1, the energy given out by A in 2 minutes. Part 2, find the energy given out by B in 3 minutes. Give it a try. Embedded in this question is also to see whether you still remember your circuit rules. You need to use one of the very basic circuit rules to find the answer for B. So the answer for A is 0.2 times 2 minutes times 3, right? Okay, no, 1.2 joules is the answer. Correct, no, Ming Guan? Why? What's wrong with I times T times V? T must be in seconds, correct. Yeah, cheap trick, dirty trick, but it works for some students. So W, which is the energy given out, is equals to V times Q, which is equals to 3 volts times 0.2 times 60. Resist the temptation to use calculator, try to use a mental calculation. 0.2 times 3 is 0.6, 0.6 times 60 is 36 joules. Multiplied by, sorry? Oh, multiplied by 2, sorry. Therefore, it's 72 joules. Okay. 2 minutes. Okay. So, quite a simple question. Try to do that for B. Try to do that for B. $144 times 1.5, that's 72, 214. 16, 14, 16? Yeah, 16, correct, 216. How? Ken? So what did you, what is it that I was testing you? The first thing I test you is whether you know that current is equals to time times the current. Sorry, charge is equals to current times time, and time must be in seconds. That's the first thing I tested you. And whether you know how to apply W equals to VQ. Third thing I'm testing you, very simple one, whether you know how to take 9 minus 3 to give you 6. But do you know why is it that the V of A plus the V of B must be equals to 9? What's the reason? Series, yeah, see, but what is the fundamental physics principle that tells you that it must die, whatever you connect things in series? There's a fundamental reason behind being series, therefore V has to add up to the EMF. Why? Remember, what does V relates to? Energy, exactly. So when I say that this is 9 volts, what does it mean? It means that in driving 1 coulomb of charge, how much energy is given to the charge? 9, which means that if 9 joules, of the 9 joules, 3 joules is being used here, the 6 joules must be the other one, correct. So the fundamental reason why VA plus VB equals to the EMF is because of conservation of energy. That's the reason why. Okay? So you must know this. And we'll go to the parallel circuits where there's certain conservation rules that apply. So I'll come to that later on. The next thing I want to go through is this thing called the electron volt. It's quite a side point, but it is also based on this, this idea about W equals to V times Q. Just that if I were to accelerate an electron from across here, this is the shorter one. So across here, this is 0 volts, say this is 1 volts. So the battery is 1 volts. I connect the ends of the batteries to 2 plates. And then I put the electron on the negative plate. What will happen to the electron? It will do this long words called A, starting with A. 4 syllable. Wow, accelerate, yes, correct. You gain energy, right? You gain KE, right? Where does the KE come from? It must come from somewhere, right? We talked about conservation energy before. Where does it come from? Work done by the battery, yes, correct. So, what's the work done by the battery? You take 1 volt multiplied by the charge of the electron, and I'm sure that you remember this value, 1.6 times 10 to the power minus 1.6 times 10 to the power minus 19 coulombs. So the energy gain is this. Now, there's a special name given to this energy gain by the electron when it's accelerated over 1 volts, and this is what we call 1 EV, electron volt. This is what we call electron volt. You accelerate 1 electronic charge across 1 volt, you get 1 electron volt. Test. What if I were to accelerate another charged particle where you got 2 protons and 2 neutrons across the same 1 volt battery, but now I switch it around so that it's plus and this is minus. So this is actually a helium nucleus, in case you can't see it. So you got 2 electronic charge and 2 neutral particles. So I accelerate it over 1 volt. How many EV does this have? How many? How many of you say it's still 1? How many of you say that it's 2? Okay, how many of you say that I don't know? Okay. You make a guess lah, make a guess. You see, if you accelerate 1 electronic charge across 1 volt, you get 1 eV. Now you accelerate 2 electronic charge across 1 volt. 2 eV, exactly. Okay, so the energy gained by this one is 2 eV. Cannot. So if I accelerate this, what's the potential difference? I must accelerate the particle over here to get 1 eV. Half a volt, yes, correct. You take the volts, multiply by the charge, then you get the EV. Understand? Let's try. If you accelerate a lithium ion, a lithium nucleus. Lithium nucleus has how many protons? 2 or 3? 2, this is 2 already. So it's 3. It's 7, 3. Yeah, 3. So if I accelerate a lithium nucleus over 4 volts, how many EV will the nucleus have? A lithium nucleus has 3 electronic charge and is accelerated over 4 volts. How many EV of energy does it have? 12 EV, exactly. Quite simple, you just take the number of charge, multiply by the volts. You get EV. Easy, huh? You won't know until you apply. So let's apply it. E, unknown, electron accelerated over, given the mass of electron is 9.1 times 10 to the power minus 31, and the final V that accumulates is 0.1 times the speed of light. You shouldn't need me to tell you the speed of light, which is 3 times 10 to the power 8. Yes, correct, meters per second. Well, I was expecting someone to say 2.9948, but it's 3 times 10 to the power 8. Yeah, so this is the speed that it gains, and I'm assuming you still remember what's the expression for Ke. Still remember, huh? Ah, fortunately no one say MGH. So given this information, this is the final speed, I would like you to find the E that accelerated. And charge, of course, you need to know 1.6 times 10 to the power minus 19 coulombs. Give me a try. Give me a shot. Yes, Aditya. C is speed of light, yeah, correct. C is speed of light. There are no other constants that is capital, oh yeah, actually specific capacity, but that's not a constant. That's a symbol. Give it a try. I accelerate the electron over there and then it actually gains a certain kind of energy. So find the V that you need. Shouldn't be too small because the speed is actually quite high. But that said, electron's mass is quite low. So if you give it a flick, probably you go really quite fast. How? Can anyone shout out the answer to me? Anyone? Come on. Some of you have the answer, just need to shout out. Come on. Wait a minute. I'm still accelerating. Sorry? 3 times 10 to the power 8. We're just talking about this, right?
It's 1.33 times 10 to the power minus 20.
Cannot be so small. Let me see. Let me try 0.5 times 9.1 to the power minus 31 times 3 times 10 to the power 7 squared divided by this. I got, squared. I got 2560 volts. 2560 volts. Which actually is not very high if you think about this. 2560 volts. Anyone got it? Or you just take half mv squared divided by the charge of electron, that's it. Which means that you just need to connect 10 of the power supply in series. It's 240 volts. Connect 10 of them in series. You can accelerate electron up to 10% the speed of light.
So then you connect 100.
And then, but it doesn't go in proportion because of relativity. It doesn't go up linearly anymore. Yeah. How do I? Half mv squared, which have everything over there, divided by the charge of electron. Why? Because work done by battery equals to K of electron equals to Q times V, which this is your E. Okay? So therefore I find the K of the electron first, then divide it by the charge of the electron. Conservation of energy. Any work that's done by the battery must be equals to the Ke of the electron. Again? Well, we can label it anything else, right? I mean E because it's EMF. Yeah, E equals to A and then EMF. Cool? Okay? Now, think about this. Am I okay? Now I'm going to extend this idea to something else. Think about this. I'm not talking about energy, but I'm talking about current. I'm going to elaborate the concept to something else. Now, say for example, I connect this device, a certain conductor, and this is plus, this is minus. What will happen to the electron inside? Hey, hello, listener. Hello, Adi, Balaji. Yeah, Aditya, stop distracting Balaji, can? Yeah, thank you. Yeah. Okay, let's focus on this. Now, when you have this case over here, or probably I will have an electron here. Now, will the electron accelerate all the way across the conductor or resistive material? Now, there are other things inside this conductor known as atoms, right? So what happened to the electron is that it will accelerate, hit here, hit here, hit here, sometimes even bounce backwards and bounce forward. So when you accelerate the electron, we apply a potential EMF across the conductor. What happens is that the electrons actually jiggle its way through. Now, even though when we say that it's 2560 volts, even if you apply a 2.5 volts battery, you'll find that the speed gained by electron is few thousand or probably hundreds of thousands of meters per second. It's really fast because the electrons are really light. However, because of the multiple collisions they experience, it doesn't move at a kind of hundred thousands of meters per second kind of speed. It will probably drift through at a much lower speed. So that is what we call the drift velocity. The drift velocity. It is different from the instantaneous velocity. Imagine that Usain Bolt has to run through the Christmas party in Orchard Road kind of thing. Even though he can run at 40 meters per second, even though he can run at 10 meters per second, there's no way he can run at 10 meters per second. He'll be ramming into people. His effective speed probably is just like 1 meter per second. Okay? So that's the idea, the effective speed of the electrons as it moves through the conductor. And I'm going to show you an equation, how you can derive an equation that relates drift velocity to certain quantities in the material. Now imagine I got a conductor of cross-sectional area A, and imagine that within the conductor I got this section L. And this section L passes through this point over here in time t. So this column of charges passes by the arrow point in time t. So the number of charge carriers, the volume of this section over here will be A times L. So okay, volume equals to A times L. Now I'm going to multiply by a quantity that you may not be that familiar with, which is called N. This is the number of charge carriers per volume. We'll talk about how to find that values later. So don't worry, we'll talk about that later. So let's assume that there's this quantity called N, which is a property of the substance. Every substance has its own N, depending on the purity of the substance. So every element has its own N. And multiply by the charge of the electron. So what do I have now? What I got here is basically the total charge in this section over here. And if I divide it by T, do you agree that that will be the current? There's charge flowing through per unit time. Think about this. What is the length per unit time traveled by the conductor? It's the length per unit time. Exactly. So this is the thing. So this is the equation that relates the current to the drift velocity and other quantities in the material. A test. If I were to have a conductor that looks like this. This is A, this is B, and I connect it to a circuit. Fill in the blanks with equal, bigger, or smaller. The current on both sides will be same. Yes, correct. It has to be the same. Otherwise, you'll be destroying charges or creating charges. It has to be the same. As a result, VA or VB is bigger. Yeah, correct. It's just like almost like water pipe lah. You tighten the water pipe, it will flow faster. Can? Now think about this. Is there a possibility that you can make it so small that it becomes speed of light? Right. I mean, you see, we say that V is proportional to 1 about A, right? If I make A so darn small, there is a chance mathematically that V will exceed the speed of light. Possible. You say cannot, obviously it's correct, but the question is why can't it be? Based on the mathematics, it seems so. My question to you is go and think about why is it that what's the other mechanism that come into play that stop it? Hey, no, speed of light is the holy barrier, it shouldn't go across. Yeah? Think about this, what's the barrier? But because math-wise, I constant, V proportional to 1 upon A. Why not speed of light? Think about this, yeah? Anyone can give me a convincing answer? I will give you, not additional worksheet, don't worry, but something that is worth your brain power. Sorry? Are you just throwing equations or do you actually have a reason why? You need to explain more. You cannot, has it got to do with physics? Oh, wow, obviously. You must be specific, yeah, Ken? Cool. So the next thing I'd like to go through with you is, do I still have any other things to go through with you? In fact, no. I'll come to a stop for this segment. Can you press the record button again?